Hi, I'm Jody Selko, and I'm back with you today to talk about phenomena. Let me share my screen so I can share with you some of the ones I have produced for my classes. You've already seen a few, but here are some more. First, I want you to notice that I've included my email address. That's on purpose. Feel free to contact me if you have any questions. So first, let me tell you about phenomena. These are real world examples or the context of a scientific idea or the scientific content. They're all around us. Many historical science experiments were based on observed phenomena. So that somebody would see something and go, oh, what's going on there? So the phenomena I'm presenting here are context for my lesson topic or content. You can also observe them and then investigate and then provide an explanation. So the first one I want to talk about is how reaction speeds change as you change the temperature. The higher the temperature is, the faster the chemistry goes. If you cook, you know this. Things cook hotter, faster in a higher temperature oven than in a colder temperature oven.
I have with me two beakers, cold water and hot water, and some effervescent antacid tablets. I just picked these up at my local pharmacy. And so what I'm going to do is put 100 milliliters of warm water on your, I don't know what side that is, and on this side is the cold water, same volume, more or less. And I'm going to take one antacid tablet and put them in each of the two beakers. This one's cold, this one's hot, and we'll see what happens. Oh, it appears that the one in the warm water is dissolving quite a bit more rapidly than the one in cold water. And so it looks like the one in warm water has completely dissolved and the one in the cold water is still going. Let's sort of see how long it takes. And so this dissolving reaction actually illustrates something else that we should have seen before, and that is the chemistry happens faster in warm than it does in cold. I have
Okay. So my next phenomena is the same chemical reaction, except this time these effervescent tablets are designed to dissolve in water. And I want to show you what happens when you change the water content of the liquid.
I can also demonstrate that the antacid that we just tried dissolves differently when it's not in water, showing that the actual reaction is with water and not with just some other liquid. I've brought with me some 91% rubbing alcohol, that's isopropanol, and the same antacid relievers. On this side, in the larger one, I have nothing but the alcohol, and in the smaller container, believe it or not, in the same volume, what I have is half water, half alcohol, and I'm going to put antacid tablets in them and see what happens. The one in the half alcohol, half water is actually dissolving and fizzing, but the one in just the alcohol doesn't appear to be doing much at all. So it looks like the one in both the alcohol and water mixture in the solution is done. It's still fizzing from the bottom, but the tablet has dissolved. And it looks like in the alcohol, the tablet itself is barely done anything at all. And while we could sit here and watch it dissolve, it's going to be about 20 minutes. So we'll stop it there.
All right. So this just has to do with displacing one of the reactants. And so this phenomenon is quite well known that the less there is for the one of the reactants, the second one doesn't complete the chemistry unless you have enough of the other reactant to join it. So here, this seems really stupid, but this is one of these examples of phenomena. I'm going to have two videos of boiling water, and it takes much longer for one of them than the other, and that's because the volumes of water are different in the same kettle, so I know that the heating is the same. In the first one, I have what appears to be 1.5 liters and then 3/4 of a liter in the other.
Welcome. Today we're going to be boiling water. In the kettle, I have 1.5 liters of water, and I'm going to turn it on and time it to see how long it actually takes to boil. So according to my stopwatch, it took 7 minutes and 38 seconds for the water to actually boil and the dinger on the kettle to go off. And once it does, it automatically shuts itself off. Did you notice the water level went up as the water heated?
Okay, so here's half the volume of water, and we'll see what happens this time.
Welcome. We're going to boil more water. This time I have 3/4 or 0.75 of a liter in the same kettle. It's been cooled down to room temperature before I started. Same cold water, same tap. And now we're going to try it again. What do you predict how long it will actually take to boil the water this time? Let's try. Water boiled, dinger went off at 4 minutes and 17 seconds. Was it about half of what it was before? I bet it was close.
Okay, so this is relatively simple, but still an example of a phenomena that you might have observed yourself. The more water you try to heat, the longer it takes to do it. So here's another one. This is chlorine bleach, sodium hypochlorite, NaOCl. And when this gets on things that are colored, it tends to remove the coloring. Chemically, it's doing this by oxidizing the colored compound. If you want to know more about that, I'm happy to explain that later.
All right, today we have some water with blue food coloring, and I'm going to add some bleach and see how long it takes to actually bleach out the blue food coloring. Okay, this reaction has been going for 12 minutes and 39 seconds, and you can see that virtually all of the color has bleached out. This is what we call a relatively slow process, Many other chemical processes are much slower than this one is.
All right, so you can do this particular reaction if you have some sodium hypochlorite bleach with anything that is organic and colored, and the color will either disappear or change to another color. Here I'm going to electroplate. What that means is that when I say it's not spontaneous, this was for a particular class where we were studying that, but this is the type of reaction like in a battery where you're recharging it. In this case, it doesn't just happen by itself like the previous ones I've shown you, except the boiling water. And I'm going to run some electricity through the paper clips off of the battery, and we'll see what happens.
I have another way that I can pull the copper out of solution by adding electrons, and that's with a battery. I have with me a 9-volt battery, a battery clip, 2 wires, and 2 paper clips, which I'm going to use as my electrodes. I'm going to connect the battery clip to the battery, and I'm going to set it down. And then I'm going to take my 2 electrodes, and I'm going to bring them in from opposite sides just to make sure that they don't actually touch. And I'm going to put them into the copper solution, and we'll see what happens. This should be quite a bit faster than the zinc, and I'm driving with electricity the reaction to pull the copper out, and you might be able to see that the paper clips are both turning brown and getting quite a bit thicker, at least the bit that's in the copper solution. And I should be able to pull all of the copper out of solution with this one battery. This is what we call electroplating, and it's the same way that you electroplate leaves to make jewelry, or chrome onto bumpers to make a nice shiny chrome bumper. So instead of having the zinc give up its electrons, it's the battery this time that's giving up its electrons to the copper, and the copper ions are then depositing on the paper clips as the electrodes as they combine with electrons. So the bubbling is occurring on the electrode closest to you. That one is where the electrons are being given off. And some of those electrons, instead of going through the wire or the solution, are actually electrolyzing the water, forming hydrogen and oxygen. And at the other end, I can see there's quite a bit of copper deposited. So instead of waiting for all the copper to actually be removed, I'm going to show you what the 2 electrodes look like. And you can actually see that this one, where the copper was depositing, got quite a bit thicker. And the other one actually has gotten quite a bit thinner. And the color's changed on both, but the copper is deposited on this one, the one that got quite a bit thicker. And that's just coming out of the solution. And this is what we call a non-spontaneous reaction, because I actually had to make it occur with a battery providing energy for it to occur.
Okay, so in a previous video, I had shown an oxidation reduction reaction between powdered zinc and copper. I'm just not showing that one here, but that one is spontaneous. That one just goes by itself, and that has to do with the electronegativity of copper and zinc, or where they are on an activity chart or oxidation reduction potential chart. So we also spend a fair amount of time on gases. And so here's a video about the gas volume and its dependence on the amount of gas.
Today I'm going to talk about Avogadro's law, and I'm going to use a very common thing that we have probably all played with. This is just a regular balloon. I'm going to blow it up about halfway. Isn't that exciting? Now, in order to increase the volume of this balloon, we all know I have to actually add more air. So I'm going to do that. Because I added more air, the volume increases. That's actually Avogadro's law.
So it may sound simple, and if you've ever done this with a tire or anything else, you know that the more gas that you add, the volume increases or it inflates because there's more stuff on the inside of it. But this was discovered by Boyle, who was an English scientist back in the 1600s. This was an observation that he made, I think probably in a syringe, um, that the more sort of gas that they put into this syringe, the more space volume it occupied. So here's another one, how the gas volume depends on pressure.
Today I have with me a mostly clear plastic gas-tight syringe. That means when I push on the plunger, the gas shouldn't be able to escape. And what that will do is pressurize the inside of the syringe here in the cylinder. I've stopped up the outlet with a little piece of broken balloon, and on the inside I have 3 mini marshmallows. And marshmallows are really good at showing what happens to the volume of gas because they're whipped gelatin, and so they've got lots of little air pockets, little balloons inside of them. So let's see what happens when I actually push on the plunger and increase the pressure. Can you see that their size is decreasing? I'm not just scooting them over. And when I release it, their volume should increase, and when I pull back on the syringe, their volume should increase. And that's Boyle's law.
Oh, so sorry. So here's Boyle. The previous one is Avogadro, who was an Italian. And I'm not sure if I know when that was, but Boyle's law, this one, pressure and volume, was done in the 1600s. Of course, not in this way. And so I want to talk about a natural phenomena that led to a chemical invention. And so this first video about fireflies is not one of my videos. This is from the National Geographic Society.
The synchronous firefly ranges throughout the southern Appalachians. It really is a pretty magical thing to see. I think people are just fascinated by fireflies, you know, especially growing up. A lot of people have experiences of catching fireflies in jars and looking at how they're doing their flashing, you know, looking at them real close. Maybe it reminds them of their youth and they want to bring their children out to experience the same thing. The synchronous firefly can be distinguished from other species by its pattern of 6 flashes about half a second apart. It may look somewhat random at first, but when you get a high density of males flashing, the synchronicity of the dark period is very obvious, and then the flashing itself will become synchronous as the night goes on. Generally, fireflies do have a similar appearance. Some are larger. The predatory ones tend to be a little bit bigger. And there's a really small species too called the blue ghost, and it's very small. But generally, they're a type of beetle, and so they're going to have this hard outer shell over their wings that they used to fly with. And they usually also have a little bit of red and yellow markings right above their head. And so you really do have to look at the flash pattern and some other morphological characters to tell the species apart. Generally, the habitat where we find Photinus carolinus is in these low-lying, moist areas where there's kind of a relatively clear understory so that the fireflies can visually see each other. It also has to have somewhat of a closed canopy so that it can be nice and dark. They typically start flashing around 9:30 or 10, but they do wait for it to get fairly dark. There's a couple of theories as to why they're synchronous, and the female really does need a large light input in order for her to respond. That's how she recognizes the correct species. So when she responds and the males then know that she's the right female, then they can reproduce. There's lots of other things that are flashing. So they have to have this sort of Morse code in order to be able to know they're with the right species.
Okay, so these are really fascinating insects if you have never seen them. I grew up in California, where I currently live, and they've never made it to the western part of the United States because they've never made it over the Rockies. But when I was a postdoc in Indiana, which is in the Midwest, they did have them, and I was just abjectly fascinated by these creatures. They are amazing. And those flashing patterns by the males are a signal to the females that they are looking for a mate. And so for years, there have been a variety of chemical companies who have paid a penny a piece or something to children to catch these bugs so that they could figure out what their chemistry was. And it turns out that many of them have a chemical called luciferin, and it's set off by an enzyme called luciferase. That's what happens in these fireflies. And the chemists set out to create some mimic of that. By the way, you can also see these bioluminescent creatures. There's a whole bunch of them in the ocean. And there are some other things that do it as well, like mushrooms. So if you look around, you will find something that will do this. So here's the chemist's takeoff on these fireflies.
So I have some warm water and some ice water and 3 light sticks. I'm going to set off the light sticks, hopefully all at the same time, and I'll put one in the middle as a control, one in the warm water, and one in the cold water, and we'll see what happens. So I'm going to mix them all up. The way these work is that they actually have an inner part that has hydrogen peroxide in it, and then the outer part that actually has the thing the hydrogen peroxide reacts with. And part of the reaction is the emission of light. So it's an exothermic reaction. It's just what they call a cool reaction. In other words, it doesn't get hot, but it is giving off energy by virtue of glowing. And we'll let these equilibrate to their temperatures and compare them and see what happens. The construction of these are all identical. So whatever is going on should all be a factor of the temperature and not actually anything else. So let me see if I can help it along here. So here's the cool one, and here's the warm one. So the warm one appears to be quite a bit brighter. The cold one appears to be quite a bit dimmer. And that's because the chemistry is sped up when it's warm and slowed down when it's cold. It's why when you cook at a higher temperature, things cook faster. I'm going to take the cold one, put it in hot one, put it in cold, just to see what happens. My control is still in the middle. So some of you may have heard that they last longer when you put them in the freezer, and that's because the chemistry slows down until you warm them back up, and then they get brighter again. They all have the same amount of chemicals in them, so the same amount of light comes out. Question is just how fast. I do like the eeriness of these guys. So that one looks like it's now dimmer than the control, and that one is brighter than the control. So it actually isn't the individual light sticks, it's actually the temperature changing them.
Okay, so as I said, there's a whole bunch of different ways that you can do this, and the chemists have learned a variety of ways to do this. If you ever come across one of these glow sticks, um, put it above your head and look towards a light, and you can see the inner ampule, the little container of hydrogen peroxide, and that's what reacts with the it's a biphenyl ester, and so it'll forms a compound, temporary compound that then gives off the light and decomposes further. So you can also examine the heat capacity, and this one is kind of interesting because it's a very different way to do this. Most physics experiments use some sort of chunk of metal or something like that.
So I have the balloon I blew up with my breath for the Avogadro's law demonstration. It has nothing but my breath, my air in it. And I have with me a sterno can, which I'm going to light. And so what I'm going to do is blow up another balloon, only this time I'm going to put some water in it first, because I want to show you what happens when the heat capacity of water is actually higher than the air. So I have added about 1 ounce of water to the balloon, and now I'm going to blow it up. So it's about the same size as the other one. So this one actually has the water in it. I'm going to show you what happens when I put a regular balloon with air over the flame. And that's exactly what we expected, right? We know that the polymer in the balloon actually doesn't hold together very well under heat. And now I have to light my sterno again. And so now I'm going to use the balloon with the water and see what happens. And it turns out, because the heat capacity of water is so much higher than air, that the heat actually transfers through the balloon into the water, and so the balloon doesn't actually burst, and you can actually boil water in a balloon.
Not everything always goes the way you expect. Just take that to heart. All right, so my message to you is find phenomena in the world around you. All you have to do is look at something and think, ah, what's going on there? Everyday objects often have an interesting story to tell, and ask lots of questions. I was impressed by the ones you were asking about my last video. My favorite question is either why or how does that do that? So here's a list of all the links to my videos, as well as to the National Geographic video about the fireflies. And I want to thank you for your attention. Please send me questions. Again, I am sharing my email address so that you can contact me. And I'm going to stop sharing so you can see me. And I wish you a wonderful, happy hunting for phenomena.